In this video, we're going to take a look at the central limit theorem and the distribution of sample means. So the last few times we've been working with the distribution of sample proportions. Now we're going to switch gears and look at quantitative data and how it presents itself. So first, recall that a sampling distribution is a distribution of sample statistics, so those calculated values coming from sample data, such as means or proportions, though it could also be standard deviations, medians, you name it. And it represents the distribution of point estimates, so estimates of the population parameter based on samples of a fixed size from a particular or certain population. So we know that sample statistics are going to vary from sample to sample, and in the case of proportions, however, we determined that the distribution could be approximated by the normal model with p hat, so our distribution of sample proportions behaving approximately normally with a center at the population proportion p with standard deviation equal to the calculation of the square root of pq over n, and this allowed us to do all sorts of fun probability calculations, run one proportion hypothesis test, and to determine confidence intervals. So how about if instead of the distribution of sample proportions, we consider the distribution of sample means? Can we also approximate this distribution with a normal model? And if so, under what conditions and with what parameters? So it turns out that regardless of the original population distribution y, the distribution of sample means will look normal provided we have a large enough sample size. So as n increases, as our sample size increases, the distribution is going to look more and more normal and the standard deviation will become smaller. Moreover, the mean of the distribution of sample means or averages is approximately equal to the population mean. So they're going to give in that distribution of means an approximation for what the true population mean is. The standard deviation of the distribution of sample means or averages is going to be less than the standard deviation of the population. As soon as we look at the distribution of sample means, right, we could have had a whole bunch of variability in the sample data itself, but when we look to the means alone, it kind of eliminates some of that variation that we had in the data to come to just a single summary value. So the variation among those summary values is going to be quite a bit less than the variability in the population itself or in an individual sample itself. So these three observations are going to be coming to us thanks to the central limit theorem. And this is a pretty big deal, and we've heard about it briefly before in terms of the distribution of sample proportions. That is a special case of the central limit theorem, where it's just assuming that we give values of 0 and 1 to yeses and nos in our categorical data distribution, right? And so when we do an average, it's comes down to being the same as finding a proportion. We do a count of all of the yeses, divide by how many things that we had or how many data values were in our sample. So we can think of them almost in the same way. So the central limit theorem is stating that the distribution of sample means is going to be approximately normal, and it's going to have as its expected value of y bar for its middle and a standard deviation of y bar for its standard deviation. Now, we're going to see those calculations done kind of separated out, so that's why we want to kind of take a look at that. So the expected value of y bars, so this is the mean of the means, is going to be equal to E of y, that is the mean of the population. Now, we have seen that otherwise labeled as mu, and we're just kind of staying consistent at this point with our expected value and standard deviation notation, stating explicitly what the center and spread is of. So in this case, it's of population data y, as opposed to sample mean data y bar. So that's where you want to keep a hold of that kind of notation difference and understand what they're meaning there. And then the standard deviation of the means, standard deviation of the means is going to be equal to the standard deviation of the population And again, we called that sigma, when we were first starting out. That is a general label also for just the normal model's parameters. So that's why we're being a little more specific here. And we're going to say that it's the standard deviation of the values of y in our population. And then we divide it by the square root of n. And that is what's going to be reducing our standard deviation of the means as opposed to the standard deviation of the population. So we're going to be dividing by a factor of square root of n to make it smaller. Okay, so this is the factor that makes the standard deviation of the means less than the standard deviation of the population. So the things that we need to make sure are true before we can proceed, so our conditions that must be met, they should all sound really, really familiar. Because again, distribution of sample proportions based on central limit theorem. So the big ideas are all the same for our conditions. Random, independent, large enough sample size. So those things are all the same. 1 and 2, random and independent, those are exactly the same checks as we've been doing before. You want to verify that the problem statement tells you that the sample was randomly selected, and we need that in order to be representative of the population we're trying to say something about. And observations need to be independent, so we check that the sample size n is less than 10% of the population size. That gives us pseudo-independence. And just like we were noticing before, it is a very rare case that we're actually using natural independence. That is only something that we look for when we're dealing with things that do not have a fixed population size. So dice rolls, coin flips, things like that. Now the piece that changes a little bit is that sample size check. We don't have P's and Q's, right? There is no proportion of success, proportion of failure in our population that we can use to verify that we've met a sample size requirement. So instead we have two possible ways to verify this. First of all, if your population has been defined as being normal to start with, then all samples that you take from it should be approximately normal, and the distribution of the means coming from those samples will be normal, guaranteed. So if you're told that the population was normal, then automatically the distribution of sample means will be normal regardless of sample size. You could have a sample size of 2 and have a distribution of sample means that is going to be normal looking. Otherwise, if you don't know that the population was normally distributed to start, then you're going to need to look to an actual sample size requirement. And we give a ballpark of, or we give a convention of a sample size of 30, and that will ensure that the distribution of sample means has overcome any non-normal behavior in the population. Now, that's kind of an upper bound situation. You could potentially be looking at the distribution and determine that a smaller sample size than 30 would overcome those features. And it is, often the case that a sample size of 10 or 20 would be more than enough. But we will stick with, in terms of our checking for that sample size of 30 when we don't know that the population was already normally distributed. Okay, so those are our 3 condition checks: random, independent, minimum sample size of at least 30, or the population was normal to start with. So let's take a quick look at an example here. We have a single dice that's going to be rolled, and its expected value is 3.5, and its standard deviation is 1.708. Now, this is the value on the die itself. We don't know that this is how many sides it has, if it was fair or not. This is just what we found by experiment, probably. And we're going to assume that the distribution of dice rolls is normally distributed. Okay, so in that case, we don't have to worry about sample size checks. We could have a very small sample size and we'd be all good. All right, so what model would we use for the distribution for y bar? That is the sample means if we rolled n 6 times. So the fact that we're being given a sample size not equal to 1 tells us that we're going to have to use the central limit theorem and look at the distribution of samples of size 6 to come up with this model. So then our expected value of y bar is just going to be equal to the expected value in the population. So that'll just be equal to 3.5. Then define the standard deviation, that's our other parameter of y bar, and watch for that notation. You need to be really careful that you're identifying the correct things that are being distributed. We have a lot of things now that we distribute, so you want to be careful with that notation. And that's going to be equal to the standard deviation in the population, 1.708, but our distribution of means will have less variability in it. We account for that by dividing the standard deviation in the population by the square root of the sample size, which is the square root of 6. Now, calculating that out, we're going to get 0.697, and I'm rounding that to 3 decimal places because that original standard deviation was given to me in terms of 3 decimal places. Please keep in mind that we're now talking quantitative data, so there isn't a hard and fast rule for number of decimal places. Just like we've dealt with the quantitative data before, you want to include at least 1 to 2 decimal places beyond what the data was given to you in. We never round to whole numbers just because that makes more sense for the data, right? If we were talking about number of children, we're still going to have parts of children in our calculation of mean and standard deviations. We would take that to 1 or 2 decimal places. But you don't go to 4, okay? Don't just blanket across the board, do 4 decimal places. You want to be thinking about what level of accuracy is reasonable for what you're calculating. All right, and so our model, remember the language, what model, define the distribution. Those things are all just referring then to coming up with what is being distributed. And since we've met the conditions, I assume we meet the conditions at least, this is going to be normal. And we're going to have as our mean of that distribution 3.5, and our standard deviation is 0.697. Okay, so whenever you're defining the model, please make sure you're showing those calculations of the parameters separate from the model itself. That's not always done in demonstrations and other books and resources, but for our class, you want to make sure you're showing me your understanding of those different parts. Okay, what model would we use for the distribution of y bar if we rolled 50 times? All right, so same basic idea, right? The distribution center is still going to be 3.5. but it's the standard deviation that gets affected by that higher sample size. So now we're going to be looking at dividing by the square root of 50. Dividing by a larger number will make that value smaller. So then we should have 0.242, and that means our model is going to be of y bars. So sample means it's going to be approximately normal, center of 3.5, and a standard deviation of 0.242. All right, now we're going to roll 100 times. Hopefully you're starting to see the pattern here, right? We're going to now have expected value of y bar is going to remain 3.5. Does not matter the sample size. We still expect the center to be at the population distribution's center or mean. And then we're going to have our standard deviation. That is what changes because of the sample size. The larger our sample size, the smaller the standard deviation will be, with, however, diminishing returns. And what I mean by that is that as you increase your sample size, because of that square root, it's not going to be a perfectly linear relationship. Eventually you kind of flatten out a bit, because that square root of x function, if you remember, it kind of looks like this, right? So you're going to see these increases, but the amount of increase in that value becomes less and less over time. So the effect of the increase in sample size will have less and less of an effect overall on your standard deviation calculation, eventually anyway. So this becomes 0.171. And our model will then be of our sample means. It'll be approximately normal, center still at 3.5. What's changing now is we're shrinking the amount of variability. We expect now our sample means to be within a much smaller distance of that center, most of them anyway, right? And so that would be 0.171. Okay, so together these values are just their means and standard deviations, just like they always have been. So we expect most samples to have a mean of 3.5, give or take there we go, 0.171. Okay, so it's that same kind of, most of our sample means are going to be within 1.71 of our approximate center of 3.5. Okay, would it be unusual to get a mean of 4.25 among 100 rolls? Okay, so we need to identify which model we're talking about. So we're talking about the model coming from part C, because we're dealing with a sample size of 100. And unusual means automatically we're calculating a z-score. So z is going to be equal to 4.25 minus the mean for the distribution divided by the standard deviation of the distribution, 171, since we're dealing with that sample size of 100. So this is where I was saying, again, we didn't want to restrict ourselves to only one way of writing the z-score formula, because in any distribution we come across, the calculation for the z-score to determine unusualness is always the data value minus the mean divided by the standard deviation, whichever model we happen to be using. And this comes to 4.39. So absolutely that is unusual. Yes, it is unusual. Now, this is always something, like, this is based on having a pretty small standard deviation, right? So would 4.39 have been unusual in the population? Now, it wouldn't have probably been, we don't know if that would have been an actual outcome, but were we to go ahead and do that one, right, we could have had, just as a side note, z 4.25 minus 3.5, and in the population, right, our standard deviation was 1.708, and so our z-score, 4.25 minus 3.5 divided by 1.708 is 0.44 for our z-score. So not unusual, right? And that's, again, coming down to that difference in our standard deviations. So when we have a larger sample size, then it becomes less and less likely that we'll see much variation between our sample means. Okay, and when we were just looking in the population, there's far more variability. Our standard deviation is much larger. So that particular outcome in our population is going to be much more likely than it would be as a mean in a distribution of samples of a certain size. All right, so let's take a look at another example. Subway claims that their footlong subs should be an average of 12 inches with a standard deviation of 1 inch. Assuming this is true, how likely is it to get a sample average of at least 10.5 inches within a sample size of 50? So what becomes important here is recognizing when we have a situation when we're looking at samples of size not equal to 1. Okay, so that's one thing we want to kind of identify right off the bat, is our sample size is 50. Had our sample size been 1, so what would be the likelihood of getting a footlong sub that is 10.5 inches within, like, the population of footlong subs, right? That would be the equivalent question. So once we have a sample size of 50, though, we're going to need to set up our distribution in terms of all samples of size 50 and what the behavior is within that. So we're going to need the expected value of the sample means, which is just going to be the same as in the population, which is 12 inches. And then the standard deviation of those sample means, that is going to be equal to our population standard deviation divided by the square root of our sample size. And I'll go to 2 decimal places on this one, just because especially in this case, the second position is pretty close to where we would have been rounding up or choosing not to. I'm just going to keep both of them in there. And notice I've also included our units. Since we're dealing with quantitative data, we have units that should be included in the end result of our calculations. Okay, now I'm going to draw my distribution. So this is normal with a mean of 12 inches, standard deviation of 0.14 inches. And what we want to be careful with now is being able to report in our labeling what these numbers mean. Okay, we're looking at sample average of at least 10.5 inches. So 10.5 inches, and at least means that or greater. And these values here that we have listed though are sample means. So this is the mean length of foot long, and n equals 50 for our sample size. Okay, so do watch for that, okay, because now we have means, we have had before proportions, we've had counts, we've had just the population values, okay? And so now we want our z-score, because this is a full normal model probability calculation. We go through all of those same steps that we have for the last number of weeks, actually. So we'll have 10.5 minus 12 divided by 0.14 to get our z-score, round to 2 decimal places, negative 10.71. Oh my gosh. We should know what that probability is right off the bat. So let's take a look. Probability, and here's another place where we want to watch for our symbols. This is now y bar, right? Because those are distribution of sample means. And we're looking at the probability that that mean is greater than or equal to 10.5, which is the same as the probability of z being greater than or equal to negative 10.71. Now with that extreme value of z, we know it's going to be one of two options, 0 plus or 1 minus. Then you look to your shading. Have you shaded a lot or a little of your image? And in this case, we're shading a lot, so we know that this is going to be 1 minus. So it is almost certain that the sample average will be at least 10.5 inches. So it is almost certain that the sample mean or average will be at least 10.5 inches. And this is in a sample of 50 foot long subs. Within a sample of 50 foot long subs. Okay, so the one thing I do want to take a moment to just remind ourselves of is what an average is. So an average ultimately, or our mean ultimately, is a replacement for what the common, most likely, average amount would be for an individual case, okay? So it really is kind of giving this broad stroke, fair share, what everybody would have, were everybody equal type of value for the group. Okay, and so that's what you want to make sure you're recognizing is this is a replacement value for a single instance if everybody was kind of kept the same. Okay, and that becomes important when we look at questions like this next one. So the Inn at Spanish Head has an elevator with a weight capacity of 2,000 pounds. If you are on the elevator with 10 other people, should you be concerned for your safety? So assume the distribution of weights is approximately normal with a mean of 170 pounds and a standard deviation of 30 pounds. So in any of these cases, the first thing you want to do is try and identify what is your sample size. So you're on the elevator with 10 other people. That means your sample size n is 11. And as soon as you know your sample size is not equal to 1, then you know that you're going to need to set up a distribution of sample means. So just go ahead and get that kind of established first of all. So the expected value of y bar is going to be equal to the distribution. And we're focusing on weights here, right? We're using the mean and standard deviation given to us in the problem. So that's going to be 170 pounds. And the standard deviation of y bar is going to be 30 pounds. Okay, notice again, we've got our units, got all up and going, divided by the square root of 11. There we go. That's going to then be 9.05, and this is still in pounds. There we go. So we've got our units, we've got our mean and our standard deviation for the distribution of sample means, but we're given a total weight, and that total weight does not make sense in terms of our distribution, because if we draw our distribution of sample means, we've got approximately normal with a mean weight of 170 pounds, standard deviation at 9.05 pounds. We know that these are the mean weights for N equals 11 people. Okay, so there's 170. And so if we tried to put a bound of 2,000 on here, 2,000, that doesn't make sense, right? It's not the mean weight, that's the total weight. So we were given a total, but our model is going to be about mean. So how can we go from a total weight of 2,000 pounds to something that is an average? Well, we just need to divide that by how many people there are, right? And that would give us the average for that group if we were going to have a total weight of 2,000 pounds. So wide bar, our bound that we'll use in this particular problem is going to be 2,000 divided by 11, and that will be 0.8 pounds. Okay, so that 2,000 didn't make sense, but we can have 181.8. And there's our pounds. And so now we want to find our z-score, 181.8 minus our mean of 170 divided by standard deviation of 9.05. Get a z-score of 1.30. Okay, so now we can go ahead and calculate the probability. So the probability, and again, these are y bars, sample means, that are greater than or equal to 181.8, and that is equivalent to the probability that z is greater than or equal to 1.30. And from GeoGebra, using, again, this is the same as usual, we're going to use the z-scores for our probability calculation, and that's going to be 0.0968. So there is about a 10% chance that let's just get rid of that, that the weight of you and 10 other people will exceed, let's see, the max weight capacity of 2,000 pounds. Okay, so that's actually, yeah, you want to kick a couple people off, because although it's a low-ish likelihood, 10% is still high enough to be a little bit frightening, right? So that's one way you can deal with the totals, is to take the total, convert it into a average, then use that as your bound for the distribution of sample means based on the sample size. Okay, so let's take a look at another one. Suppose that the weights of checked baggage follows a nearly normal distribution with a mean of 45 pounds and a standard deviation of 3.2 pounds. What is the probability that a randomly selected checked bag weighs less than 40 pounds? Okay, so again, first thing we want to do is think about sample size. We are talking about a randomly selected checked bag. So that means n in this case is equal to 1. When we have a sample size equal to 1, we're going to use just the good old population distribution. Use the population distribution. Okay, we're not going to need a distribution of sample means because we're not able to calculate a mean on this, or at least the mean that we would calculate is equal to that single value. So we don't need to worry about it. That means we need our expected value for the distribution, autopilot there, distribution of our population data, and that'll be 45. And this is weights, so we're looking at pounds. The standard deviation of y, that's going to be given to us. That's 3.2 pounds. Do not have to do any extra calculations there. Our bound y is that 40 pounds. We can then look at the distribution in terms of the image. That is normal, 45 and 3.2. This is checked bag weights. Checked bag weights, and that is in pounds. So there's no n needed in this description of the data that we're distributing here. These are weights and in pounds. So there's 45, 40 is over here. Less than is what we're calculating the probability for, so shade to the left. Now we need our z-score. That's going to be 40 minus 45 divided by 3.2, and that's going to be negative 1.56 negative since we're less than the mean, which should make sense. And then we have the probability that y, not y bar, is less than or equal to 40 is equal to the probability, that z is less than or equal to negative 1.56. Use the negative 1.56 in GeoGebra with 0 and 1 for the parameters, and that will give us 0.0594 for our probability. So there is about a 6% chance that a bag will weigh less than 40 pounds. Okay. Now, what is the probability that the average weight of 10 randomly selected checked bags is less than 40 pounds? So notice here we've changed from having a sample size of 1, looking at a bag, to looking at a group of 10 bags. So n is going to be equal to 10. As soon as we see a sample size greater than 1, we know we're needing to come up with a distribution of sample means. So that means we need to go ahead and calculate the mean and standard deviation for that distribution. So that'll be the expected value now of y bar. That is the same as the mean as in the population, so that's 45 pounds. The standard deviation of y bar is the standard deviation in the population, but we're going to shrink that. The standard deviation in the distribution of means is always smaller than in the population. Otherwise, they're exactly the same. And then what is different between those two questions, right? That's the other thing you want to be asking yourself. And so that will be divided by the square root of our sample size of 10. And then that is going to be 1.01, and this is in pounds as well. So then we've got our model. This is normal, 45 pounds for our center, 1.01 for our standard deviation. So there's 45. And remember, we need to change the labeling here. We're talking about the mean weight of 10 checked bags. So this is the mean weight of 10 checked bags. Okay, and then our bound is going to still be 40 pounds, but remember that is y bar is going to be 40 pounds. So there's our 40, and we are looking still for less than. So other than being in a different distribution, our problem is the same. So it's helpful to kind of look at this and go, well, what is likely to be the case? Are we likely to see a similar probability, or are we going to see less than or greater than probability? And the fact that our z-score is going to be changing based on that standard deviation should guide you to kind of what's going on here. So then our z-score is going to be the 40 minus 45. That's the difference from the mean divided by the standard deviation for this distribution of means, negative 4.95. So you can see that this makes a huge difference now because our standard deviation is so much smaller in the distribution of sample means than it is in the distribution of the population. When we're doing a count of how many standard deviations that same value of 40 is from the center, it's going to be a lot more of them when we're taking a smaller and smaller ruler measurement, right? So now we can go ahead and calculate the probability in GeoGebra. So the probability of y bar being less than or equal to 40, and that's equivalent to the probability that z is less than or equal to negative 4.95. And in GeoGebra, obviously it is such a big z-score, negative, but still big, right? We're going to have 0 plus. And I know that just from looking at my picture, because my picture is shading a smaller amount, less than 50%. So when I have that large of a z-score and I'm shading very little, I know that will be associated with a almost no chance of happening as opposed to an almost certain chance of happening. Okay, so there is almost no chance that the 10 bags will have an average weight that is less than 40 pounds. Okay, what is the probability that the total weight of 10 bags is greater than 470 pounds? All right, so that's the next one. And we're looking here at a total. So when we have the total, we're going to want to make sure that we are converting that into an average, because we don't have a model for totals, right? We don't have a way of coming up with means and standard deviations for that given value. We are still talking about 10 bags, so that's going to guide us to which model we're going to need to choose. We're going to use sample means, and we're going to do our calculation based on that. And lo and behold, we already have. So this is the same as in part B. So we're going to be able to just draw this out. This is normal 45 and 1.01. And this is the average or mean. Stick with mean, actually. Mean bag weight in N equals 10 bags. There's 45. Now we need to find out what our bound is. So we need to take the total. So total weight, that was equal to 470 pounds. So the average weight, or our, in this case, Y bar that we're going to use for the model, is that 470 total divided by our sample size, and that's going to give us 47 pounds as our mean that we're going to be using. So there's 47, and we want greater than, so we're shading to the right. We need to find our z-score. Z is going to be 47 minus 45 divided by 1.01. Now again, we're going to see that our z-score is going to be smaller than that last case. We only have a difference of 2 pounds between the mean and our bound, but our standard deviation is approximately 1, so we know that the z-score will be approximately 2, and it does come out to 1.98 on that. So it's not unusual, barely, but it's not unusual. So we should expect a probability that's probably around that 2.5 mark, right? That's going to be cutting off the tail for greater than 2 standard deviations from the mean based on that 68, 95, 99.7 rule. So probability that Y bar is greater than or equal to 47 pounds is equivalent to the probability that Z is greater than or equal to 1.98. Use 1.98 in GeoGebra, we'll get 0.0239. So there is about a 2% chance that the total weight of 10 bags is greater than 470 pounds. Okay, and that's kind of it for the new perspective on this calculation of means, or calculations of probability and z-scores and unusualness. We've just changed up the model. But since we're in a normal model distribution, keep in mind that we could be looking for percentiles. We could be looking to find the bound instead of the area under the curve, or the probability. So all of those calculations that we did back in the day just about the normal model itself with the population could still apply here to our distribution of sample means as well. So don't let that kind of trick you up too much. Review some of that material. We are getting close to the final exam, so it's a good time to take a look back. All right, we'll see you in the next video.